Good afternoon, welcome. Welcome at the new session, new week. How is everybody today? Good? Okay, I can see thumbs up. You can also use the, yes, hello, the chat box, the conversation box, and then I will know that you have a keyboard next to you and you're ready to answer all of my questions. Okay, you can always give me a signal. Okay, let's see what we will do. Last week, we did start chapter 10. We did go through the 10.1 sequences. That was the introduction. Yes, we remember a beautiful Fibonacci sequence and lots of connection with golden proportion, like golden ratios. And of course, the rigor for determining if the sequence is convergent or divergent. And then 10.2, we did start the infinite summation, infinite series. That's when I hope we know the main difference between the sequence and series. And then the rest of the sections, actually today is the new one, we will try to develop a couple of tests, how to test the convergence or divergence of the infinite series. Okay, and now this section is quite long, and I'm really hoping you did watch the video about the comparison test, limit comparison test, and the integral test, because I'm explaining, I am proving all of these tests, I'm explaining the reason behind, and probably I'm solving a couple of questions, because now I would like just to focus on practicing, of applying these tests. Okay, it means I hope you will be okay, and you can definitely, if you didn't watch, yes, after the session, you can revisit the videos about the tests, because that's all of the tools that we need. What we learn in section 10.2, we did learn, that was the introduction, and we also learned one of the important type of the infinite series, which was the geometric one. Yes, we remember the geometric one, and the geometric one is quite straightforward, because as soon as we identify, we can find the common ratio. And if the common ratio is between -1 and 1, we know that the series is convergent, and we have even the formula to find the sum. Well, that's simple. But not all of the formulas that we will see are the geometric one, are the nice, obvious one. We will have a couple of different things, different mathematical expression, and we still have to identify convergence or divergence. Also, what we learn, which is actually I supposed to mention as a first tool, we did learn the very, very first test, that even if we have lots of other tools, tests, the first test that we always have to check is the nth term divergence test, which actually I will call test for divergence. Okay, that's mean when you see my solutions, especially for the written homework, if I will say test for divergence, this is the nth term divergence test. I think it's just easier and faster name. And what this test is telling us, if we will grab the formula, and if that corresponding sequence, the limit, the behavior at infinity is different than 0 or does not exist, then it's no chance for convergence. Yeah? The infinite series is divergent, and that's it. Yeah, that's easy. But if the limit is 0, then we know nothing. Yes, we have to remember. For instance, if I will ask you this one, is this infinite series convergent or divergent? 1 over n. It is divergent. Why is divergent? It's definitely divergent. Divergent. And yes, I don't know if you had the proof, but when we start adding the terms 1 plus 1/2 plus 1/3 plus 1/4, Yes, Deepan, we can definitely use the integral. We can use the integral test, but we still don't know. Yes, I mean, I hope we know, but because this was, I'm still referring to the section 10.2. In section 10.2, we didn't know. That's mean what we were trying to do. We were trying to look at the partial sums. Yes, we also know what it is. Like we can try to, because when I expand this, yeah, it's 1, and then it's 1/2, 1/3, 1/4, 1/5. And when we start adding like 5 terms, 6 terms, 60 terms, 100 terms, we will see that that new sequence, the sequence of the partial sums, actually are getting bigger and bigger. We accumulate huge number. That means this sum definitely goes to the infinity and it's divergent. However, my point is, this is like one of the special infinite series. Somebody remembers what is the name of this one? 1/n, and it's just this one, just 1/n, no other like form. It's the harmonic series. Thank you. Harmonic. That's, please remember, harmonic series is definitely divergent, and but what is also a good to notice, and we also use this as an example. If I grab that formula 1/n, yes, and if I will check the limit at infinity, 1/big number is 0. That means even if the limit is 0, yes, we may have a divergence. That means the main sentence is, the main statement is, if the limit of the sequence is 0, we know nothing about the convergence or divergence. We have to use just different like tools, different tests. Right? But if the limit is different than 0, no chance for convergence. It's always divergent. Test for divergence. Yeah, and term divergence test. Okay, but that harmonic series is definitely divergent because I will refer quite often. Okay, that's what we know. Let's actually start. What I have, I have these tests. That's mean, again, I hope you did watch the session. You can definitely watch, check the proof, what I did, how I'm like proving this to back up my claim. But what we have to know, we just have to know the test and know when to apply and how to apply. Oh, Zander is asking the question about the quizzes. I think we got the email, yes, from Caroline. That's mean you can check the email. Yes, we do. We end up having just by small, like, yes, like including the material, because all of the tests is sometimes here to including the material from this week. That's mean what we have in week 5, we have a quiz that is related just to the sequences. Yeah. And then it's a normal quiz. It could be just the sequences. However, we did have section 10.2. That's when we did create additional sequence, additional quiz. But as per the class conversation, the email, you know that is for extra credit. That means just small bonus. Okay. But yes, in general, we have 2 quizzes. You don't have to take the other one. It's just optional. Yeah. You have the main quiz, which is the weekly quiz worth 10 points, week 5 quiz, and it's, I think I name it like sequences only. That means that's the quiz that it's part of the final grade. The other one is additional. You don't have to take it. Okay, but of course nobody will miss it. We all need some extra points. This week, week number 6. Okay, let's check. I will check with Caroline. Oh no, this week, that I'm just talking about the week number 5. This week, I have to check what's going on. It's supposed to be 1 quiz. Maybe she's okay. No. This week you will have only 1 quiz. Yeah, that is part of the final grading. Just 1 quiz. Please, give me a couple of minutes after the session. No, it's supposed to be 1 quiz. Okay, I will check. Oh, okay. I was thinking that you're still asking for that week 5. Okay, let's start. Okay, because we have to be confident. Let's check if we are confident. Because if you're confident with all of the examples that I will solve today, that's big part of the midterm. And we know we have midterm in not next week, we will still have a new material week after. Yeah, so fast. Everything is like, yeah. Summer is always goes so fast. Okay, that's an integral test. If we will look, yes, if you will have an infinite series, A sub n, yeah, summation, A sub n. And now, if you will, like, not now, the test for divergence will not work because the limit is 0. Then what we can try, we can look at this formula and we can check if this expression is like continuous, positive, and decreasing, okay, on that interval, as a function, of course. Then we may try to integrate. Yes, it will be the improper integral. We remember section 7.7. And now, if the integral, the corresponding integral, is convergent, then the infinite summation is convergent. If the integral is divergent, then the corresponding series is divergent. That's it. They're not exactly the same, okay, especially for the convergence. If you will integrate this, okay, then let's say we will get convergence, you will get a finite number. This is not exactly the same like the summation. We may compare, you can check the video, okay? You can check my proof. We may like compare, but it's not the same. But we still have this justification. Okay? That's nice and easy, but we have to make sure that the function is satisfying all of this condition, all of them, especially positive. All of them. No, none of them is like stronger than the other. Continuity, positive, and decreasing. Of course, continuous. We know that is discrete, but we will think about the corresponding function. Okay, that's integral test. We will use, especially if the formula looks like attractive for integration. And you have practice from integration. If you know, I know how to integrate, you can integrate and get the answer. And then you can say, okay, if the integral converges, the series convergent. And so, okay, that's the first test that we will possibly use. Another test that we have, it's called P-series test, which sometimes mathematicians, they will still say that this is the integral test. Okay? They will still say integral test, because it is based on the integral. But when we will see this form of this like series, 1 over n to the power of p, p could be any positive number. Yes, actually any number. Any number. I don't have to restrict this to the, could be any number. P could be any number. Okay, because we may actually have negative also. That means P could be theoretically any real number. But now we remember from the improper integral, because it's based on the integral. And you can even grab, yes, you can even grab this x to the power of p. Yeah, that was, yeah, definitely proven in section 7.7. And if you will integrate, yes, we remember what's happened. If that value is greater than 1, we will always get convergence. If it's equal to 1 or less than 1, then it's divergent. Okay, and you can, yes, you can check this. But, and we just, it's easy to know this, use this as a tool, because nobody will ask you to prove it. We have to just apply this test, use the test, know the toolbox, use that tool. Yeah, but we will call P-series test because it's kind of like, yeah, it's the nice form, but it's definitely consequently from integral test. Okay. Another test that we will use today, and I cover, yeah, comparison test. Right? That's mean comparison is quite, yes, quite also nice. Integral test is quite time consuming sometimes, but if we can use comparison tests, so nice and quick. But let's see what we will have. Suppose that the series A sub n and B sub n are the series with the positive terms. That's you probably noticed the integral test, the P-series test, now comparison test, we can only apply if all of the terms are positive. No negative 1 to the n. That's alternating, and that's some of the terms are negative. That will be tomorrow, next section. For now, 10.3 only talks about the infinite series with positive terms. Okay, we good with this. Because if some terms are alternating, we will be not able to compare. And now what we do, what we can compare, really quickly. You also have a really detailed explanation in the video. Let's assume that we're looking, this, always when I start, my pen is, that's our original question, A sub n. Let's just make some details. And now, if we will notice that this formula A sub n is like similar to something that is known, that is obvious, that is easy, because the job for us is to find out the new formula. Okay, and let's say I will create B sub n, similar to A sub n. And I can think about these two B sub n and A sub n expressions. I have to make the relation, like which one, substituting n, 1, 2, 3, 4, increasing, which one is greater, which one is smaller. And let's say I will say this fraction is definitely always like A sub n is always greater. And then for the same number of terms, with the sigma, we also hold this relation. Okay. And now, if we have to figure out this one. And now, as I said, this will be like obvious, and you will know, okay, this infinite series is convergent. Convergent. Okay, that's mean now we can, I hope it's like a common sense. If this one is convergent, oh, am I, okay, no. Let me do it the other way. That will be easier. This is my formula. This will be the new one. This is that's our question. This is our formula. This one we will create. Okay. And this one we know that is convergent. Okay, easy one, we figure out it's convergent. And now let's look. If this one is convergent, means that it's like the sum exists as a finite number. I hope it's a common sense. Everything what is smaller, it is also convergent. Please tell me that this makes sense. Yes, because we can see that like our exercise is this one to figure out if A sub n is convergent. And then if I will create this comparison, I can figure out, okay, B sub n is convergent, and everything what is smaller is also convergent. If you will figure out B sub n, but the relation and the B sub n is convergent, but for some reason the relation is this way, we cannot use comparison. Because if this is convergent, the sum exists as a finite number. Something that is greater, I don't know, could be greater, still could be convergent, but could be also infinity, could be divergent. Okay, then we will not, use we will not use this comparison test. We actually call this one direct comparison test. That's when we cannot directly compare. Okay, we cannot directly compare if it's this, but if it's this way, we can compare it, no problem. Or another version, that's mean this is this one. Another version is we do have infinite series A sub n. We're creating similar formula because we know that B sub n, similar to A sub n, is actually divergent. And then we're looking at this expression, we figure out that this one, our series is greater, then for the same number of terms, this will be also greater. We can also make the comparison. If this summation is divergent infinity, we may think this way, everything what is greater is also infinity. That means we can conclude that this is divergent by directly comparing, by direct comparison test. If in case of divergent, if the inequality will be the other way, we cannot compare. Okay, that means everything is explained here. And this is the test. That means only a special relation and convergence, divergence will let us compare this, use direct comparison. This one will be good and this one will be good. That means this one is also, I can say, convergent by directly comparing, direct comparison test, okay? Okay, that means that's the way to use comparison. If the direct comparison test doesn't work, we can also use the limit comparison. Okay, that's, oh, let's wait with this. Limit comparison is telling us this, that we still figure out the new formula, B sub n, to compare, but the relation will not let us to compare, right? Then what we're doing, we grabbing this formula and creating this ratio, A sub n over B sub n. A sub n is the original problem. B sub n is something that we figure out to compare with. When we compute that limit at infinity of that ratio, and we're getting a finite number C, then we may conclude that both of the series behaves the same. If the known one was convergent, our question is also, our series is also convergent. If it's divergent, it's divergent. Yeah? Please check the video because I'm explaining the details. And this one could be a little bit confusing, but it's a nice test. If this limit is 0 or infinity, if you extremely well understand this test, you may use it. Yeah, but it's only for in one condition, for 0 for convergence, infinity for divergence. But if it's finite number, we may conclude both. Okay, and okay, that's all of the tests. That's all of the tests for today. And what I also have, I think I create, you probably checked, if you checked section 10.5 is the summary of all of the tests, okay? Because I will recommend to make a list. And I have to type, yes, I type this. It's called strategy, but it's just the test. You may notice this is the n-term divergence test, which by Kasia, it's called test for divergence. Yeah, that's when you know the test. Then you learn the geometric one. This is supposed to be the integral test. I have to integral test. Okay, integral test. I will put, and the P-series test is supposed to be just a small box. I will correct this. Okay, we know the integral. Let me actually, this is the integral. Okay, convergence, integral, divergence, series, divergence. That means I will actually make this, yeah, and then direct comparison and the limit comparison. And this is half of my page. The other half will be the test with negative terms. But that's later, that's tomorrow and next week. Okay, for now, we have to know this. Yeah? Geometric, integral test, P-series test, comparison, limit comparison. Okay, and then that's the negative, but that's tomorrow and that's next week. And that will be all of the tests. Alternating series test, ratio test, and root test. Okay, one thing that I skipped is this one. Yeah? Since we have to create a new formula for comparison, that's me. Let's see. Yeah? We may imagine that each of this expression has a sigma, is a series. For instance, when we will see something like this, yeah, 2 to the n minus 1, 3 to the n plus 5. It looks like geometric. It's not geometric, right? But we may ignore this constant, yeah? Or even if this is like n is also slower, yeah, the relative rates of growth. I can only pick up this and I can compare. Yes, I can just grab 2 to the n, 3 to the n. This one is the geometric one. Yeah, if we think about the series, can you tell me if this one is convergent or divergent? In the series 2/3 to the n. We have to know this like no thinking. It's convergent, thank you. You may, okay, let's see this. Oh, where am I? Where is my, okay, this, yeah. You may possibly take a picture, or you can check this on Canvas. Yeah, you can see that's this. Yeah, geometric common ratio less than 1 between -1 and 1 convergence. Okay, where is my list? Here. That means this one is definitely convergent because the common ratio is 2/3. Okay, and then something that is smaller is also convergent. That means when this will be the summation, I can say this infinite series is convergent by directly comparing with this. Oh yeah, that's the same. Okay, second example. When we have a ratio of 2 polynomials, we may only grab the leading terms, because we know algebraically, calculus-wise, the other one at infinity will disappear. That means n to the power of n to the 4, n to the 6. When we simplify, we will get 1 over n to the power of 2. Do you think? And what about this one, 1 over n to the power of 2? It is convergent or divergent? Convergent, thank you, by the p series. It's convergent because the p is 2 greater than 1, convergent. Everything what is smaller is convergent. Also, another thing, are we okay to put this relation to this inequality, this direction? Do you see that the fraction on the left-hand side is actually smaller than the right-hand side? Because you can see we adding something in the denominator. If the denominator is greater, the whole fraction is smaller. Yeah, that's algebra class in middle school. Yes, if the denominator is greater, the whole fraction is smaller. And we even subtract. That means if I subtract something from the numerator, I'm making even smaller. Yeah, that means definitely obvious like direction of the inequality. Okay, this is also a standard comparison. When we will see the formula with arctangent of n, we can always say all of the terms are less than pi over 2. Yeah? This could be just part of the formula. Yeah? Sine of n, cosine of n, we can always replace and put 1. Then we're simplifying the formula, and it's, this one, am I right with this one? Because e to the power of 1 over n will be e to the power of 0 if n is infinity, n is big. But it will be e, square root of e, cube root of e. Okay, it's getting smaller and smaller, but the limit is 1. That means all of the terms are greater than 1. Yes, I'm just testing if the inequality is okay. Okay, that means something like this. Okay, 7 and 8. We may say, yeah, let's look at this. This is actually really nice. Even if it is -1 to the n, it's still positive terms, yeah, because it's 5 plus 1 or 5 minus 1. And if we need the direction this way, we can say it's less than 6 or it's greater than 4. Yeah, -1, +1. Natural log of n, we may compare to 1, we may compare to n, we may compare to any power function, but k could be, let's say k could be any number. Okay, or even if I take both to the same power, always n, that power function will be logarithmic, will be smaller. Okay, if I flip this, I have this. That's a couple of like ideas, but theoretically you can compare with everything you wish you see. Okay, let's start. But lots of practice is required, lots of practice. Okay, that's the only question. I mean, the same question, I will just change the formula. I will show you the formula, and my question at the moment is if the infinite series is convergent or divergent, and what test we use. Okay, this one is number 1. And if you have some formula, let me know. Yeah, we can also put it here. It will be good source of problems. Okay, we're starting. And I also have a couple of on my notes, which I didn't type. Okay. Infinite summation for n plus 1 over 3n minus 1. Convergent or divergent? Everybody use this. Okay, Deepen is saying divergent. Can somebody back up that claim? Let's use that time, okay? Let's spend next half an hour on the intensive, yeah. It is correct, it's divergent, but why is divergent? Oh, what is the first test? Nth term divergence test, but I will say test for divergence, okay? If I will see that you're using that, this means that you really was like paying attention on my live session. Test for divergence, or it is definitely nth term divergence test, okay? Nth term, let me just say one, the first and the last time. Nth term divergence test. Oh, my writing is the same thing. Because what this test is telling us, and that's how we always have to start, we're grabbing the formula and testing the limit. What is this limit? Is this limit 0? This limit exists as a finite number, different than 0. Yeah? If the limit is different than 0, yeah, or infinity, or does not exist, the infinite series is divergent. And do we understand why? I hope, because now when we will think, okay, we can substitute instead of n1, we will have the first term. We can substitute instead of n2, we will have a second term, because I don't want to do the arithmetic. We will have the third term. But now, how the terms behaves like at infinity? We can see they are finite number. They are almost like 4/3, 4/3. 4/3, and we will be keep adding. You have to think that we will keep adding that number because it's summation, it's a sigma. Adding 4/3 infinity many times, of course, is a big number. That's the reason that if the sequence converges, that sequence converges to 4/3. But when I keep adding this, when I put sigma, it's divergent. That's the essence of the test for divergence, nth term divergence test. We are comparing it with real. Oh, no, we're not doing any comparison. Somebody asked me, but you may send the message to everybody because I think you sent just to me. We're not doing any comparison. Yeah, no comparison, because that even comparison will not work. Oh, I mean, the comparison can give us divergence. We may try actually comparison if you like. But no, this is definitely, we really should not even think, okay, that's mean comparison. As I said, we may just focus on, but let's see. That's mean this is my new formula on the right-hand side. Yeah, I decided that is similar. But when we simplify this formula, it will be just constant, which actually sigma summation of 4/3 means that we keep adding 4/3, like 4/3, 4/3, 4/3, 4/3. That means this is definitely divergent. Yeah. Now let's see if we can compare. We subtract, because I need this inequality. We subtracting something from denominator. When I subtract something from the denominator, the fraction is smaller. No. When I subtract, when I make denominator smaller, the fraction is bigger, and I'm still adding something. That means this is definitely greater. Yeah? The expressions, sigma, sigma, we always have to say for the same number of terms, because when we keep adding, I can't add just a couple of terms. That means, this is divergent. Everything what is greater is also divergent. That means I can conclude divergence. This is divergent by direct comparison test, and we comparing with this. But yes, it's okay. But this will be, I would say, it's a little bit weird. This will be the preferable, because as soon as the limit is different than 0, divergent. But yes, it's actually good job. We can also say direct comparison. Yeah, thinking about this method. Okay, example number 2. Infinite summation of like the series of nth root of 4, convergent or divergent? Depends, say divergent. Yes, of course it's divergent, because what test? That's what we have to do. We will check the limit. And term divergence test, of course, which I will say test for divergence. This is 1 over n, 1 over big number is a small number is 0, 1. Limit different than 0. Then we have to think, okay, 1, we will be keep adding 1 plus 1 plus 1 plus 1, huge, divergent, no chance for finite number. Okay, example number 3. Series 1 is summation, sigma, yes, 1 plus 3 to the n, everything to the power of 2n. Do we remember that formula? I will grab this sig3. I will grab this sequence and compute a limit. What is this limit? Yes, limit, that's also that's good practice for the sequence, yes. 1 plus, that's n, and we may have coefficient a and coefficient b. E to the power of a times b. You can definitely check section 4.5. Improper, I mean indeterminate form, power form, and I did solve the long way. Yeah, it was, yes, we can do the E, but we don't have to, you can do the long way because it is indeterminate form, is 1 to the infinity. That's when we're supposed to go through the long way, the L'Hopital rule at some point. But if you remember that limit, that's n, it will just save our time, so save our life. Okay, that's when this is e to the power of 6. E to the power of 6, different than 0, divergent, test for divergence, and term divergence test. Nice. Because we can picture e to the power of 6 plus e to the power of 6 plus e to the power of 6 and so on. Okay, that was example number 3. Example number 4. Oh, what is this summation? What is this series 1 over n? It's harmonic one, of course, and it is, we know that it's divergent, but look at this, the limit is 0. Then what I can say, test for divergence is not applicable. If the limit is 0, we know nothing. Now it's the moment to use different tests. But this one is, yes, we can even say P series, we can say this, but since this is that one special one, test use, even if you will say it's not really a test, but even if you will say harmonic, that will be still good justification. Series. Of course, you can say P equals to 1, and then we can see P series test. Or we can say integral test. Yes, integral test, because we may still integrate 1 over n, yes, is positive, continuous, and decreasing, and then we can integrate, and the integral will be divergent. Yeah, that's when you can say anything. Yeah, but I'm not going to use the integral test because we know that it's divergent, harmonic. Okay. Okay, example number 5. Big ratio of 2 polynomials, n squared minus 4n plus 1, and then n to the power of 4, 5n cubed plus n plus 6. Do you know right away what we will do? Or maybe you know the answer. You have to know the answer. Yes, of course, Emilio. It will be basically P series test, n squared, comparing. Actually, we will compare because we see something big, but we know that we can definitely grab the leading terms. Okay. When we simplify, what I did, something. Where Where is my... Oh, that's better. When we have this simplified form, that means this one is known, it's easy. It's convergent, okay, by P series test, P equals to 2. Yeah, it's greater than 1. That's the test. But now that's not our test. This is our tool to compare. Let's figure out which fraction is greater, because if the direct doesn't work, okay, then we have to maybe use the limit comparison. What do you think? We took n squared, we took n to the power of 4. Is this fraction smaller? Do you see that this one is smaller than this one? And of course, thinking about sigma, sigma is a summation of the same number of terms. Okay, it is smaller. Thomas, are you showing to me something? Let's see, we adding something, adding. We adding something to the denominator. If the denominator is greater, the whole fraction is smaller. And we subtracting, we adding this one, but you can see just add 1 doesn't really make the fraction bigger. That means this fraction is definitely smaller. Okay, that means if this is a finite number, everything what is smaller has to be the finite number. So we can say it's convergent, yes, by direct comparison test. And in case of the comparison, we have to say what we're comparing with. We actually have this. That means I can say convergent direct comparison test. Right? Just in case if you will have drop-down menu on the test, bigger denominator, whole fraction smaller, yes. Yeah, but this is the answer, is not convergent because a P series test comparing with. Yeah, that means the test that we use directly on this is direct comparison test. Okay, let's keep working. Well, yeah. Example number 6. Infinite series from 1 to infinity, arctangent of n over n squared. What if we use the limit, yes, if we use the limit, please tell me what is the limit, because we supposed to do test for divergence, end term divergence test. What is this limit at infinity? Arc tan of n over n squared. It is 0, right? Because it's kind of like pi over 2 over n squared. Because all of the terms, let me just put, it's just a little bit informal. Arctangent of n, all of the terms are less than pi over 2. That means they not grow. N squared will grow. That means constant over big number is 0. Okay, that means test for divergence is not applicable. If the limit is 0, we know nothing. That 0 means that the terms are approaching 0. But maybe the 0 is not fast enough, like we remember from improper integrals. Direct comparison, of course, we will use, yeah, I can copy this, and instead of arc tan of n, I can put pi over 2, and all of the terms are less. Arctangent is less. I didn't change the denominator. And this one, constant, is fine. I can put in front. That's when we have 1 over n squared multiplied by pi over 2. But 1 over n squared, the p-value is greater than 1, is convergent by p series test. It's actually integral test, but it's fine. And the inequality works. Everything what is smaller than the finite number, it's convergent. That means converges by direct comparison test. Okay, converges by direct comparison test, and we comparing with this one. Yeah, we compare direct comparison test with this formula. Or the first one, the same thing. that pi over 2 must be part of the formula. Okay, good, good, yeah, good practice. Okay, numbers, did I have number 7? I have something. Okay, number 7. Sine square of n over n squared. What we can compare to? Yes, we can say 1 is the maximum value. I can put equal to because sine could be 1, and I'm not changing denominators. I don't even have to make the description. On the right-hand side, we have convergence, p-series. Everything what is smaller is convergent by direct comparison test, and we comparing with 1 over n squared. Okay, perfect. So fast, we can see this. What about this one? Oh. Oh, no, I don't, that will be... no, it's okay. I will not, because then we need another test. I wanted to change the denominator. But okay, it's fine. No. Too fast. I'm thinking too fast. Okay, number 8. Let me check. Okay. Natural log of n over n. So now, what we can do? We may try to compare with something, because comparison is basically the easiest one. If we know the right formula. Normally, we can try 1. And we're just starting with 3. You will notice that when we have natural log of n in part of the formula, we usually start with 3, because after e, the formula satisfies all of the conditions. Before e, and e, it's the fraction, like 2.7. The first integer after number e is 3. That's the reason. Okay, yes, Emilio said 1 over n, but let's check. 1 is definitely, when I think about function, like values, that's natural log of n. Yes, of course, the dots, natural log of 1, 2, 3, 4, and so on. That's natural log of n. 1 will be just 1. Yeah, that means this is just 1. That means 1 is definitely, and we can see that's e. That's e, which makes sense after 3. That's me, yes. Then, oh no, yes, correct. Oh, maybe this works. Why I didn't think this doesn't work? Is the inequality correct? No, something is wrong, or maybe I have just natural log of n is greater. Natural log of n is greater than 1. Correct, yes. I just, and then, okay, then what we have on the right-hand side? Yeah, we can compare this. Yeah, let's say natural log of n and 1. This is definitely greater because 1 will be 1. 1 is not changing. We have harmonic, we have divergent. Oh, why I was thinking that we have to use integral tests. Maybe I just messed up something. Too many formulas. Okay, yeah, overdoing is also not healthy. Okay, divergent, and now please tell me if we can use the comparison. This is divergent. Everything what is greater, it is divergent? Yes. Okay, that means this is divergent by using direct comparison test, and we compare with harmonic. Or let's say 3, because we can see starting from it. Yeah, this one will be divergent. It's definitely divergent. Yeah, divergent, but Oh, okay, because before comparison, we usually talk about the integral test, and then we can actually integrate also easily. Oh yeah, integral test will be also a good test. Divergent by direct comparison test, but it's important what we're comparing with. Okay, it's extremely important, 1/n. But integral test will be also good because natural log of n/n is continuous positive decreasing. We may prove decreasing, but it is definitely decreasing. And improper integral will be divergent. But yeah, direct comparison, we don't have to. Sometimes we can use more than one test, yeah, but we only have to list one. Okay, and then actually, do you know, I don't have the formula, but let me write for you. What about this one? 2 to the n, 3 to the n minus 1. What about this one? 2 to the n over 3 to the n minus 1. Is this infinite series convergent or divergent? We may, yes. If you can tell me convergent, it is convergent, yes, but we have to be really careful. We have to be really careful, Deepen, what test, because this is one of the catchy like formula, okay? We cannot say because we use geometric, it's not exactly geometric. We can compare to the geometric, because that -1 is messing up the formula. But yes, you partially right, partially. Smaller, greater, I'm just thinking. We can definitely grab the leading terms and it ends up being the geometric expression, geometric series with the common ratio. Common ratio is 2/3. It's actually 2/3 is absolute value is less than 1. That means this one is the geometric series convergent. Convergent. Okay. Now, if our original formula is smaller, then we can conclude convergence, because everything smaller than a finite number, it's finite number, it's convergent. But let me erase this. Which fraction, 2 to the n over 3 to the n, or this one, 2 to the n over 3 to the n minus 1, which one is greater or which one is smaller? Let's think about this one, okay? Left is greater, because when everything is the same, just -1. Subtracting something from the denominator, that's been making denominator smaller, the whole fraction is greater. And if this one is convergent, yes, convergent means like finite number. Something greater, we don't know. Could be infinity, could be divergence. That means the thing is, direct comparison test is not an option. Okay, that's we cannot really say convergent by the geometric series. No. Convergent by comparing to the geometric, yes, but not directly. Limit comparison, yes. That's mean now let's actually try, because if the direct doesn't work, limit's supposed to work. Let's actually practice this one. We have to check the behavior at infinity of a sub n, original formula, over b sub n, the new formula. And if this limit is a finite number, then both of the formulas behaves the same. Check my reasoning and in that video about the limit comparison. Okay, that's what we have. We have 2 to the n, 3 to the n minus 1, 2 to the n, 3 to the n. And let's simplify, because that's a little bit messy. 2 to the n, 3 to the n minus 1, and then dividing by fractions means multiplying by the reciprocal. And what is this limit? 3 to the n over 3 to the n minus 1? Yes, it is 1, it's a positive number. Then we can conclude that both of them, yes, doesn't matter, because we're not comparing directly. Both of them behaves the same. Okay. Do we know why we're doing this? Like why this is that justification? That means now we can say it's convergent by the limit comparison test, and we still need the formula. I can write this way. Yeah. Because we remember, I hope we remember the limits at infinity. Yeah. Do we remember the limits at infinity? Like when we had ratio of two functions, usually ratio of two polynomials. Really quickly, like if the denominator was like had higher degree, do you remember like the ratio of two polynomials? If the denominator was winning with respect to the degree, what was the limit at infinity of that ratio? If the denominator was like, oh, you don't remember? 0, yes, thank you. Because I don't want to use our precious time. Yeah, like let's say x squared plus 1, x cubed plus 5. Yeah, denominator is winning, the limit is 0. If the numerator is winning, what was the limit? Like if the numerator, like let's say this will be x to the power of 20, it will be, yeah, let's say it will be infinity. Now, if let's say 3x squared plus x minus 1, 6x squared plus 5x plus 1, limit at infinity. What is this limit at infinity? It's a finite number. Yes, actually 3/6, 1/2. Because what is my point? Oh, the battery is. Let me check why my battery. 1 second. Oh, no. Let me. Oh, no. Okay, I did plug my computers, but it's for some reason it's unplugged. Okay. Let me just say, that's when we can see this. The limit is here, the limit is the finite number, and we may say that both of the functions on the top and in the denominator, numerator and denominator, they behave the same. They have like the same, yes, the relative rates of growth, x squared. But we may also think the other way, 1/2, finite number, limit at infinity, we have finite number. What this means that both of them behaves the same. The same for that limit comparison. Finite number, yeah, we want positive. I mean, all of the terms are positive, that's mean. But finite number, then we may conclude backwards that both of the functions, the expressions, the series in this case, from the numerator and denominator behaves the same manner. If that was convergent, the other one is also convergent. If the other one will be divergent, our new one, it also has to be divergent. Okay, that's the idea of behind the limit. Okay, and we good? That means this is the correct answer. Limit comparison test, not direct, not geometric one, not P series, not no integral, just this. Okay, okay, and I don't have it. Do you have some formula? What else? How would you solve this one? 1/n natural log of n to the power of 3/2. And let's say 3. We know it will work if c is less than 0. No, let's say, okay, I don't know your name because it's RPP550. No, it will be also always because comparison test, just comparison test. And actually today's section 10.3 only works for the series with the positive terms. That means nothing will be less than 0. Okay, I answer the question, because if you see, yes, nothing, that's the reason that we say, because all of the terms are positive. Okay, number 10. What we can do? Oh, this one, yes, because this one we may also try to compare. but I think none of the comparison. Okay, we will do the integral, but let's say if I will put 1, yes, we know that 1 is less than natural log, but now we are in the denominator. That means I'm actually using this comparison. 1 is definitely less. That means if the denominator is smaller, the whole fraction is bigger. Or maybe we can do it. Oh, no, we can't do it. Because now let's see what we actually got. We do have 1 to the power of any number is 1. Okay, let's say 3. 1 over n, divergent, right? Something that is smaller, we don't know. Yeah, that means we do have divergence on this side, something that is the expression, the summation that is smaller, could be divergent, could be convergent. That means this one, direct comparison test will not work, and the limit will also not work. You can check. Okay, now we may try. Yeah, that's how, like, we don't know what to do. Because I know somebody recommend integral test and we can do it. We may also replace ln of n with n. Or maybe this will work, n to the power of 3/2. Because when we have natural log of n and n is greater, right? Because this is natural log of n, and n is just like x. That means n will be greater, n natural log. If n is greater, denominator is greater. If the denominator is greater, the whole fraction is smaller. Okay, but now let's see what we have. We do have n to the power of 1 times n to the power of 3/2. We will have 5/2. Please tell me, is this infinite series convergent or divergent? This one. Yeah, that's how we can like figure out. It's convergent. P-series test is definitely convergent. And what about directly comparing? Something that is greater, do we know? Greater than the finite number? No, that's this inequality again. Direct comparison test will not let us. If you will try limit, it will not work. You can try the limit. We will probably get 0 or infinity. We will not get finite number, positive finite number. No, that's we can see doesn't work. Yes, and that's kind of like standard. We may even increase the n to the power of something, but that's standard comparisons. Then let's see, I can copy this. This is still example number 10. And this could be even your part of your, like justification. Natural log of n to the power of 3/2. Do you think we can use the integral test? That's the corresponding function. We have to, because test for divergence also doesn't work. I supposed to maybe say somewhere, test for divergence doesn't work because limit is 0. I think you can see I eliminate all of our tools. It's not a geometric one. X ln of x to the power of 3/2. That means this function, when x is greater than 1 and even greater than 3, it's definitely positive, continuous, and decreasing because only denominator increase. Okay, we may integrate from, let's say, from 3 to infinity. Okay, what method we will use? How we can integrate this? I can rewrite t goes to the infinity. It's the, oh no, the L'Hopital rule is for the limits. Now I think we have to integrate. Chapter 7. Yes. No. It's so many things. It's so many things. We can get confused. I think I even got some. Yeah. Okay. I think the U substitution will work perfectly. U is ln of x, 1 over x dx. Perfect. This means what we have. Oh, I supposed to write line after line, but it's okay. 1 over x dx, that means it will be integral of u to the power of 3/2 du. This will be natural log of 3 and natural log of t. I'm just changing the limits of integration. Okay, but what we can say, I can still integrate, but 1 over, we can actually finish this. What is this integral? 1 over u to the power of 3/2. Let's actually write here. Okay, natural log of 3, natural log of t. It will be u to the negative 3/2. Let's integrate. We know the answer because it's like a p-value. But let's prove it. Just in case if this will be your written assignment, then we have to have all of the terms. Okay, I need the integral ln of 3, ln of t, the new limits. Yeah, I hope we're okay with this. Okay, what is this integral? We have to add 1, it will be negative half, negative 2 u to the negative half. Let's evaluate this limit. Is this finite number? Negative 2 over square root of u. Okay, limit. Okay, negative 2 square root of ln of t minus negative 2, I can put plus because we're subtracting, lower limit, square root of ln of 3. That's actually finite number. Okay, what about this one? Square root of natural log of t. What natural log of t does when t is infinity? Yeah, when the input increase is infinity. And what is negative 2 over infinity over big number? Constant over big number is a small number. And this is just a finite number. We don't even need that number. We may say the integral converges. Okay, and if the integral converges, the corresponding series convergence. I'm just showing up because it's the, yeah, that means it's definitely convergent by, let's say, IT, integral test. And we have the full proof. Okay, but please, yeah, also, please, this is important. I did kind of like poorly, maybe. Not poorly, slimly, like two, but it's positive. You can even, if this will be your written assignment, please put the whole like word positive, continuous decreasing. We good to apply the integral test. Yes, that means it is, yeah, it is convergent by integral test. Okay, integral test. I like the shortcuts. Integral test. Really nice example. Okay, I think we did 10 of them. It's quite, yes, quite okay. If you can go through and do them again, like maybe in the quarter of the time that we spent, it will be good practice, yeah, before your midterm. Because